What is the deal with these audio taper pots? What are they and where do we use them? I'm Professor Fiore and I'm going to explain it to you right now. A common question I get from people is, hey, I've got a schematic and it specifies I need an audio taper pot, but I don't have one. I only have a linear taper pot. Is it okay for me to use that instead? Well, the short answer is yes. The circuit will still work. Nothing's going to explode. However, the action of that pot, its sensitivity, let's call it, is going to be a little funky. So let's take a look at this. I have a potentiometer set up here just as a voltage divider. That's it. And you know, I'm going to tell you right now, that's a primary use of an audio taper pot. A volume control. This is what a volume control is. This is all it is. Back here, you know, I have a simple 10 volt DC source, but this would be your audio signal, right? It's coming out of, you know, a radio or some other kind of device to produce some music, tunes, whatever. And now I need to tap off a percentage of that, which is going to be fed to my power amplifier, right? So we rotate the knob, we get the tap up here. I get a lot of signal, it's loud. Rotate it the other way, counterclockwise, goes down here, very little signal, not so loud. Pretty straightforward. So, you know, when we look at, you know, a pot like this in the simulator, I'm setting this at 50%. So that means that the wiper arm is halfway up, kind of the way it's drawn. And of course, that means this 10K is split into a 5K and a 5K. That's all it is. It's just a 5K, 5K, in other words, a 1-to-1 voltage divider. And I would expect to get half of whatever I put in at the output. Now, just to prove it, what the heck, there it is, 5 volts, all right? And as we monkey with this, you know, we get different levels, right? I put in 10%. Run that again. And we should get 10%, right? 10% of 10 volts is 1 volt. All right, not too magical, you know, not too crazy. So let's say you go and get a linear pot. Standard, stock, very common linear pot. And this is going to be set up for a volume control. And, you know, you plug this in and everything. It's still going to, as you rotate the knob, the wiper arm is still going to go up and down, and you're still going to have volume that goes up and down. And that's all fine, well, and good, right? What's the problem? Well, there is a practical problem. And that is, this all has to do with the way in which we humans hear stuff. So you're probably familiar with this term decibels, right? Sound pressure level in decibels. The first thing you have to understand is human hearing is sort of super logarithmic. That's the way I'm going to describe it. And decibels are log based. So we use decibels as additive and subtractive when we want to go with powers. In other words, when I want to multiply something or divide something. So in other words, I just add a certain amount for a certain factor. Doesn't matter how big it is or how small it is. It's the factor that counts because that's the way in which we hear. I'm interested in a sound being subjectively twice as loud as another sound or 5 times as loud as another sound. And that's how we perceive sound pressure level. When we get back to electronics, 3 decibels represents a doubling of power. If you were to increase power by a factor of 10, that would be 10 decibels. Now, power varies as the square of voltage. So because this is log based, a square turns into a factor of 2. So if you double the voltage, you get a 6 dB increase. And if you increase it by order of magnitude by a factor of 10, you get a 20 decibel increase. Now, at the other extreme, I need to talk about a just noticeable difference. In other words, I'm going to compare two sources that are identical, except for their sound pressure level that they're producing. I need about 1 decibel to be sure, to be confident that one source is louder than the other source. If I have, two sound sources and I'm switching back and forth between them and the difference in sound pressure level is only, 1/4 of a dB, I can't perceive that difference. It's too small. 1 dB, yeah, most of the time we can. Now, human hearing is not like this perfectly linear function. So this actually depends on the frequency that you're listening to, in other words, the pitch, as well as the sound pressure level, in other words, its loudness. So sometimes a just noticeable difference might be a fraction of a dB, might be, 0.8 of a decibel. Sometimes it'll be maybe 2 decibels, all depending. But, 1 dB is a nice sort of round figure. We can use that as a general purpose number. As long as we're not at the extremes of frequencies, as long as we're not at something that's extremely loud or extremely quiet, 1 dB is a good rough rule of thumb, okay? Now, the final thing I want to point out is, this is where the idea of sort of super logarithmic I use comes from. To double the loudness of something, in other words, if I'm listening to a stereo and I say, well, I want this to be twice as loud, that does not take a 3 decibel increase. Yes, the power is doubled. In other words, if the stereo is pumping out 10 watts and I crank it up to 20 watts of output going to my loudspeaker, that's a 3 decibel increase. But that will not sound twice as loud to your average human. To do that, to get twice as loud, you will need somewhere in the vicinity of 8 to 10 dB. And that will depend on, again, what the source material is. But, there you are. Let's say it's up around 10 dB. Nice round number. Well, what did I just say a moment ago? A factor of 10 in power is 10 dB. So if I'm listening to my stereo at 10 watts and I want it to subjectively sound twice as loud, that 10 watts has to get bumped up to about 100 watts. Okay? Now, here's where the problem comes in. A doubling of voltage is a 6 decibel increase. That's not twice as loud. Why am I pointing that out? Back here on my voltage divider, if I have this at 50% rotation, that's half the total voltage. Half the total voltage. 6 decibels. So I want you to imagine a knob, right? A volume knob right here. And it's going from 0 to 10, right? 0, no, all the way up to 10. Right in the middle, 5. This is what we're saying. 0, nothing. Perfectly quiet. Crank it up to 10, max. You put it in the middle at 5, that's the 50% point. You're only getting a 6 decibel change from 5 to 10. All the other change is from 5 back down to 0. So that's a little odd, right? You turn your stereo up to 5, and you say, well, I want a little bit louder. You crank it up to 7, 8, it's only going to be a few dB. It's not going to be much at all. You crank it all the way up to 10, it's only going to go up by 6 dB. It's not even getting twice as loud from 5 to 10. On the other hand, if you were to decrease it, right? If you went from 5, let's say down to 2.5, that's also a factor of 2. That's also 6 dB. So in other words, from 2.5 to 5, well, that's a 6 dB change. From 5 to 10 is a 6 dB change. From 1 to 2, because that's also a doubling, from 1 to 2 is also a 6 dB change. So when you rotate the knob, what you find is when you're down toward the extreme end of counterclockwise rotation, in other words, you're down towards 0, little tiny movements in the pot produce big changes in volume. But when you go to the other extreme, big changes in the pot don't make very much loudness change at all. So if you put a linear pot in where an audio taper pot is specified, this is the problem that you're going to have. So the whole point of an audio taper pot is to non-linearize what's happening with the resistance in the upper piece versus the lower piece. And we can do this very nicely with a graphic. That characteristic is referred to as a taper, right? So we talk about a linear taper pot, an audio taper pot. We also talk about reverse taper audio pots. Basically, it's a question of how the resistance varies as you move the pot. So I've got a little graphic over here, rotation percent versus the divider percent. So the very first circuit that we looked at, right? This is the percentage of the voltage that you're getting out, and this is the percentage of your clockwise rotation. So if you're fully counterclockwise, nothing. You're up here at max, fully clockwise, then hey, you get 100%, right? So the blue line right here is linear. And if you were halfway rotated, you would get half the signal. So what we do is we distort the way in which the resistance is distributed across the rotation. Red here is a log taper pot. Now, I have to back up here just a little bit and tell you that there is no such thing as an absolute log taper audio taper pot. And those two terms, log and audio, are used synonymously. You're getting something here that sort of approximates a logarithmic characteristic. And different manufacturers will approach this in slightly different ways, slightly different shape of curve. Somebody's log curve might be a little bit lower than the red one. It might be a little bit higher than the red one. But basically, when you get to 50% rotation, typically the voltage percentage that you would get would be about 10%. Instead of 50%, okay? You return the pot to 5 on a 0 to 10 scale. You turn that pot to 5, and you're not getting 50-50 on the resistance. You're getting 10%, 90%. And when I say 10%, 90%, just to be clear about it, what I mean is this piece up here is the 90%, and this piece down here is the 10%. It's also possible to get a reverse audio taper where that's flipped, 10% up here, 90% down here. And the shape of that curve is the green curve. Those are not nearly so common. Audio taper pots, quite common. So here's how it works. You turn this thing to 50%. We get back to our little rules of thumb over here. You turn that thing to 50%, and with 10 and 90, you're only getting 10% of the total change, right, in voltage. Well, a factor of 10 in voltage is 20 decibels. So now, from 5 up to 10, that represents a 20 decibel change, rather than what we saw initially with the linear pot, which was a 6 decibel change. So that sort of stretches out the resistance change, even though it seems like you're kind of squishing it, right? Because it's 10% instead of 50-50. It's 10-90. But again, human hearing is this ratio characteristic. So by doing this, you sort of spread the decibel change out much more evenly around the rotation. So you bring it up to 5. Instead of being 6 dB down from max, it's 20 dB down from max. End result, you have more control as you get up toward 10, and the setting of the pot is much, much less touchy when you're over on the low end of the pot. Things kind of spread out. Ideally, what you would like when you rotate the knob, right, is a certain degree change, let's say like 5 degrees or 7 degrees or 3 degrees, some percentage is a certain number of dBs, right? There's a certain number of decibels as you rotate. That's ideally what you would like. And there are potentiometers that can control that very well. You pay a good penny for them. General purpose audio pot is not super well controlled like that, because after all, most people are going to just adjust the volume control subjectively anyway. It's not like maybe if you're in a high-end mixing recording studio, you need some decent accuracy on there. Or certainly if you're doing some kind of instrumentation work, you need much higher accuracy. So you go out and you buy yourself the audio taper pot. You get the 1090 instead of the 50-50, and things work well. But if you're prototyping a circuit and you don't have an audio taper pot, as long as you have the right size, if they say, give me a 10K pot here, as long as you got a 10K linear, you can put it in there and, at least continue with your prototyping. You just have to understand that the rotation is going to be a little touchy on one end and kind of insensitive on the other. Now, that's fine for a volume kind of pot, but there are some applications, some very specific applications where that's not quite right. Things might get a little funky. But really, the vast majority of applications for an audio taper pot are literally as a volume control. So that takes care of, probably 98% of what you're going to monkey with. Now, manufacturers can make all kinds of crazy tapers, right? You're not limited to just these three, which typically an audio taper pot is called an A taper, and a linear is called a B taper, and the reverse audio or anti-log is referred to as a C taper. But technically, they can make all kinds of crazy stuff, and they will, which you might need for, like I said, maybe an instrumentation situation. What do you do? I mean, if you're just monkeying around in your little home shop there, prototyping stuff, and you're not going to go into major production, right? You can't call up a manufacturer, a potentiometer manufacturer, and say, hey, I want a one-off. I want you to make 2 of these pots for me that have some kind of unique taper. Okay. I guess they'll do it if you want to throw them enough money, but, generally speaking, that's not what people are going to do. So what would you do if you are interested in some kind of weird taper? Well, it is possible to add some components and make custom tapers. And I will show you that in an upcoming video. And until then, this is Professor Fiore saying, take care, have a good one.